Okay, page 294, section 5.4. It's called the fundamental theorem of calculus. We developed it before. Now we're going to mess around with it. And he spends a little bit of time developing it, but I have a little arrow to myself over on page 295 in the middle, right in that 10 box. It says start here. That's where we're starting. Because that statement right there is the fundamental theorem of calculus, which says that if you take the derivative of such a thing, that is a function written as an integral, dependent upon this stop point of a function. Sorry. I have a dummy variable in here. When you take the derivative of an integral, you get what's inside here, which is just f of x, f evaluated at x. That's the rate at which the area is changing at x, is the function at x. It's the length of the next line. Okay? Now, listen to this next paragraph. This is pretty important. It's amazing how much you see here that you don't realize. The theorem says that every continuous function f is the derivative of some other function, namely the integral of that function. It also says that every continuous function has an antiderivative. And it says, this is the most important part, and it says that the processes of integration and differentiation are inverse. Just like this. You take the log base 10 of 10 to the x, you get x. Those are inverse functions, logging and exponenting. If they have the same base, they undo each other. Just like this. You derive an integral, derivative, integral, right next to each other. You derive an integral, what do you get? They undo each other and leaves you with the function. Just like here. Okay? They're inverse operations. Probably already figured that out because if you have a position function, you derive it to get velocity. If you have a velocity function and you want position, you have to integrate it or derive it, same thing. They undo each other. Okay, now example 1, I'm going to focus and drill into the details here a little bit. Look at example 1. It says, find the derivative of the integral from negative pi to x of cosine t dt. Anybody? Cosine x. You'll notice that maybe you haven't paid too much attention to yet, but you'll notice that this down here just needs to be a constant. This needs to be x. This can be any constant. And it doesn't matter what it is. That's a weird thing. We'll discuss that in a few minutes too. But do you see that you have that situation from negative pi to x of the cosine of t? You're deriving that integral, and so you get the cosine evaluated at x. That's the length of the next bar. That's the change in the area. Are you with me or not? Okay, so what's the next one? 1 plus x squared. And you're going, that's kind of dumb. Nevertheless, very powerful. Okay. This one says, now to find the derivative of y, if y is 1 to x squared cosine t. That's different. That's like saying, like here you get x. It's, well, no, it isn't quite like that. Never mind. I'm not going to say that. So now we're going to do one that's a little bit different because now we're going to integrate from 1 to x squared of cosine t. And we wish to take the derivative of that with respect to x. That's what they're asking us to do, though they didn't write it this way. You see that there's a little bit of a hiccup here because we're not going from some constant to x, we're going from some constant to x squared. Notice what the answer is. The answer is 2x cosine x squared. So if you want to memorize a rule, I'll show you why it works in just a minute here. If you want to memorize a rule, what you do is this derivative of this integral, they undo each other, and you end up with the cosine of x squared, yes. But then the chain rule requires that we multiply by this thing's derivative. The chain rule. Remember, ultimately we're taking a derivative. the derivative of this function. And so if we evaluate it at x squared, we have to also have to do a du dx. This is u. You know what I mean? Would you like an explanation of that? You don't have to have one if you don't want, if you can buy this. We okay with it? Okay. I can explain it further if anybody wants to. We can take a look at it. Take a look then at example 3. This one says to evaluate the integral from x to 5 of 3t sine t dt. Well, actually not evaluate. Find the derivative of it. So again, we are deriving an integral, which means it's going to undo the integral in some way or another. But now we've got x down here and 5 at the top. And I'm not going to write out f of x. I'm just going to write it right here. It's just some function we're doing, and it doesn't quite, it doesn't quite look like what we expect. How can we fix it?
Just swap those and make it negative.
Yeah, swap those and make it negative. Exactly. This is the same thing as the derivative with respect to x of the integral from 5 to x. So long as we put a negative on that, we can switch the order of operation, the order not operation, but the order of integration. And then we'll put that in, 3t sine t dt. Now remember, it's this. It's not dx minus. It's not anything like that. It's the derivative of the opposite of this integral. 3t sine t, is it? Is that what I said? Yes?
Yeah.
And so we would say that that is negative 3x sine x. Done. Okay, so we use one of those properties. Next one gets a little messier. Use that. Okay, the next one wants us to do this, integrate from 2x to x squared. The derivative with respect to x of the integral from 2x to x squared. Now we got x's on both ends, 1 over 2 plus e to the t dt. And you guys may have already looked at the solution. I wish you hadn't, and if you haven't, don't look. Let's see if we can use properties of integrals to rewrite this in this form, some way or another. And I'm just going to call this f of x for the manipulating. We'll bring this back in detail when we get done fixing this, because this can't be done with this, because we've got a function of x down here and a function of x up here. This says you integrate from a constant to a function. We had functions on both ends. So what we could do is rewrite this using that one that I said is so obvious. See if you can, let me show you which one we're looking at. See if you can figure out how I might do this. I'm talking about the one that's called additivity on page 285. That's the property we're going to use. We already used the property up above to switch the order on the previous one. But now on this one, we're going to try to use the additivity. Why don't you look at that? Look at the details of it. It's on page 285, for those of you listening. Can you see how we might use that here? What we have is something like the right side of it. I wish to split it up into two integrals like the left side. If I split that up, you see that I could write the one with this at the top as the integral from, what constant do you want to choose?
It doesn't matter.
It doesn't matter. I'm going to choose 0 just because that's one we, okay. Negative root 2, but then, is that okay? To x squared. I'm just showing you it doesn't matter of f of x, which I'll bring back in a minute, dx. I better use t's just so I don't confuse you too bad. Okay, and what could I do so that this plus what, or subtract, whatever, this thingy combined with the next thingy I wrote will give me this. How can I write the next one?
From 2x to negative root 2.
Yeah.
Like this?
Yes.
Yes.
Really?
I think it needs to be a negative increment. Because you need to get that 2x to the top.
right, but also not. I don't know.
Maybe we don't want to keep this one. Do you want to change this one?
Keep it. What was
We can do the negative thing, give it 2x to the top.
What's that?
Do the negative integral, right? Give it the 2x to the top. The 2x
Maybe.
is gonna have to be on the top spot.
Maybe. I think, yeah, get this on the top, but then what goes down here?
root 2? Negative root 2?
So,
I was just wondering if Jeff or Kyle came. Did Jeff ever come in? No? Okay, thank you.
did you guys say before 2x to root 2?
Yeah.
Negative root
That's
2?
what we have said.
Will that work?
Yeah, close.
You don't need the two.
Can you subtract it with it?
We don't need the what? You don't need the 2x on the top, is that what you're saying?
So don't we need the two X on the top?
I just want to use that property first. We got to, what I'm saying is the property says that whatever we integrate from and to here, this one has to start where this one ended, or the other way around.
Switch orders. Have that
Oh,
one
so
first,
you want this one first?
and then the other one.
Okay, so this is a rewrite, folks. If I put this one on the front, 2x, because it's down on the bottom here, to negative root 2, whatever, it doesn't, that part doesn't matter. And then here, start this one at negative root 2 and
X squared.
go to x squared. Do you see that that satisfies the condition of that property I was having you look at?
Yeah.
Okay,
Would
So-
you not get the same answer from both of those though?
would you?
Well,
Both
they're
of
both
them?
together.
Having,
But it doesn't matter what word it is. Does it?
no, I didn't.
So would you add them or subtract them?
Both at the same time also. No.
But then in the actual equation, would you have to make?
Do you want to add these together?
Yeah.
So what we're saying is that the integral from 2x to negative root 2 will give you a certain area. And then if we start the next area that we're adding to it at negative root 2 and go to x squared, wouldn't that give you the same thing as this?
Yes,
Yes.
but then you
Can-
can make the negative thing, the 2x to the top by making the first one negative, but that would still work. Then-
Because now we're trying to make it, both integrals fit this.
Yeah,
And the first one doesn't fit this.
but can you do that?
Sure.
So now we'll switch it.
Easy.
So then you just slap
We
it
need
in.
both of those integrals and we can treat separately because it's addition, Natalia. I'll talk to you about that later. I can't talk to you about that in front of Genesis. Okay, but we can treat those each separately and this one fits the bill. It's from a constant to a function. This one doesn't. So we do this.
No more.
Are we okay on that now?
Yeah.
All good.
Now, without, so I can save myself, because I'm locked onto this board, I'm going to replace these now with the function that we're actually dealing with and see what we can do. It is 1 over 2 plus e to the t. And we are deriving this. We had to set it up properly so that both of those integrals, we use the additivity property so we could get a function off the bottom and the top. So we have functions only at the top. That required a change of sign here. And this part down here makes no difference so long as it's the same. We have to start and end it in the same place. Each integral. So now let's apply the fundamental theorem to each of these separately. What will this one be?
Negative 2 over 2 plus e to the x.
Yeah.
I'm going to write down what you said and see if people agree.
But would it be either 2x?
What?
Would it be either the 2x? I get the 2's at the
4x.
top.
So you want to change this?
Yeah, the 2x.
No, leave that.
No.
I want that guy next, but the top I want it for.
No, you don't, because it's a 1, and then you have times the chain rule by
Well,
2.
chain rule,
Yes,
first top one's 2 and the second one's 2x.
what's 1 times 2?
I haven't done the second one yet, Landon.
Oh, my bad.
Do you think that replacing that x that we had there with 2x is correct, according to Kyle?
Yes.
Why? Because Kyle's right a lot of the time?
Yeah.
No, he is right. He is right. It's because when we evaluate this, when doing a derivative of an integral, it undoes the integral, but all t's get replaced with this. Times this is derivative, which is here. And there's the negative.
So the 2x.
Oh, the negative, the 2x.
The 2x.
So like if that was 4.
That'd be negative 4 over e.
Because the way it is landed.
Is there anybody who does not understand the three pieces of this? This is the derivative of this. 2 times 1. Here's your negative, which was on the front of that integral because we had to switch gears there. And all t's in the evaluation of the derivative of the integral, all t's get replaced with what it's going to, the function. So this is this one. This is correct, right? Okay, can you do the next one? 2x. And is this still plus? Yeah. Now, some people look at that and go, oh, we have the same denominator. No, you don't. And I would not recommend you try to find one. Ooh, that's good.
That's the answer.
I like that.
Okay?
Got you.
But this takes some work, folks. If you're taking the derivative of an integral, where the limits of integration are from a function to a function, you got to split them up, change the sign on one of them as you invert the limits of integration so that both of them meet that requirement, which is from a constant to a function. And then don't forget your chain rule. That's pretty crazy one, huh? Okay. Continuing. Whoops. Maybe back to 5.4. We'll go back to 5.2.
I guess so it's like Thursday one. What is Thursday? That's just how we usually go Thursday, but today I was like, I'm gonna be done Wednesday.
Okay. Let's see some other things that might come from this.
We were all
And
sleeping.
then Jared was gonna come up and be like, say Thursday, my friends, like he doesn't. But Jake.
Okay, all right, okay.
I've literally, I know, Jake comes up, literally just working the office, he says, you have 5 minutes with current, he like slams it and then walks through his office and we're all like, okay.
Thanks a lot, Kyle. This is supposed to be a professional production.
Oh, my bad. Now we're talking about
All right, so you remember the fundamental theorem because I need more board space. Maybe not so much for this one, but as I go along. This next thing you're gonna see is gonna be so weird to you. Your first exposure to it. You're gonna go,
That's kind of how.
it feels like it's cheating. And it does feel like that. But listen to this. It says, example 4 says, find a function y equals f of x. So we're looking for a function whose derivative is tangent x and also goes through the point 3, 5. So here's the deal. We're looking for a function whose derivative is a tangent x. And for the sake of notation and understanding this completely, I'm going to change this to f prime, and we are looking for f. So I'm putting it up here because we're used to seeing f and then f prime in our experience so far, right? We're trying to recover this. And we understand that if we have a derivative, that the way to recover the function it came from is to integrate it, which is an antiderivative, right? And so f of x, this guy up here, is going to be the integral of tangent x, some way or another, right? That's how we're going to find it. And that's a function itself. This function is defined as an integral, and we need for it to go through the point 3, 5. In other words, f of 3 equals 5. When we finally recover the function, it has to go through the point 3, 5. Watch this. You're going to hate this. You're going to go, that's just cheating. I'm going to make it go from 3 to x and add 5. I just forced it to go through that point.
Oh.
Because when x is 3, the integral from 3 to 3 is 0. I don't care what you're integrating. The integral from 3 to 3 is 0. So when x is 3, if I add 5 here, I have just forced this function to go through the point 3, 5. Tricky.
Wow.
And a lot of people would look at that and say, okay, so now integrate it. Now finish it. No, this is done.
What?
Do you know why this is done? Because there's nothing more to do. I don't know of any function whose derivative is tangent. There is one, but I don't know what it is. In other words, when I'm anti-deriving, what I'm trying to figure out is what thing do I know whose derivative is tangent? I don't know of any.
It actually lists it in the back of the textbook.
I know, thanks, John. But I don't know of any in my head. But based on the fundamental theorem that we just read, this obviously has an antiderivative because on certain intervals anyway, tangent is continuous. It's continuous on its domain, which means it has an antiderivative. But there's nothing more to do, nor do I need to do anything. I don't have to do any more. I have found a function that goes through this point whose derivative is tangent. That was the goal. It's just that the function is written as an integral. It feels like it's cheating because you didn't do anything, really. You didn't do any math. Well, we did a lot, really. It's just conceptual, and there wasn't much to do on paper. Okay, that one, you'll have to do a couple of those like that. If you don't know the antiderivative, you can still write the antiderivative as a function, but you leave it in integral form. It means if I knew a function whose derivative was tangent, this would provide the graph of it. Okay? Now, I want you to go down to, oh, by the way, the derivative or the antiderivative in this case, if you wanted to actually antiderive it, and I don't expect you to know how to do this, but the antiderivative is provided for you in the middle of that page. It's also in the back of the book, John. It's the natural log of the absolute value of cosine 3 over cosine x plus 5.
Well, that's what I was thinking. Yeah.
I thought it was cosine 2 over cosine 3.
Okay? So that's what you get if you were to actually antiderive it and use skills you're going to learn a little bit later. We'll come back to this and show you that exactly where it is. It's not going to be that hard when we get there. But here's the discussion. Listen, you guys, because you live in the era you live in, you don't understand how cool these tools are that you have. Listen to this discussion at the bottom of page 297. It says, consider for a moment the two forms of the function we have just been discussing. That is the recovered function from 3 to x tangent x, or the integral from 3 to x of tangent x dt plus 5. And the other one, which you have no idea how to come up with yet, is the natural log of the absolute value of cosine 3 over cosine x plus 5. And then consider both of those, they're both true. It says, with which expression is it easier to evaluate, say, f of 4? And the right one would be easier to evaluate because at least you got something to plug it in. Right? I mean, correct?
Yep.
Okay. From the time of Newton almost to the present, there has been no contest. The expression on the right is easier to find f of 4 because you got something to plug it in. At least it provides something to compute, and there have always been tables or slide rules or calculators to facilitate the computation. In other words, we can find the cosine of 4 with a calculator, a slide rule, or a table of values. At least there's something to compute, okay? The expression on the left involved, at best, a tedious summing process and almost certainly an increased opportunity for error. Summing, drawing rectangles and summing it up. Today, we can find f of 4 from either expression on the same machine. The choice is between nint of tangent x with respect to x from 3 to 4, add 5, and the natural log of the absolute value of cosine 3 divided by cosine 4, close it, plus 5. Both calculations give 5.4151 blah, blah, blah in approximately the same amount of time. We can even use nint to graph the function. This modest technology feat would have absolutely dazzled the mathematicians in the 18th and 19th centuries, who knew how the solutions of differential equations such as dy dx equal tangent x could be written as integrals, but for whom integrals were of no practical use computationally unless they could be written in exact form. Since so few integrals could, in fact, be written in exact form, nint would have spared generations of scientists much, much frustration. Nevertheless, one must not proceed blindly into the world of calculator computation. Exploration 1 will demonstrate the need for caution. Again, you must remain the master of your calculator, not the other way around. So we're gonna show you how the calculator could kind of take over your thoughts here a little bit, or maybe not. And we're actually going to use this function and try to nint it. So in your calculator, first thing, I want you to go on a negative 10 to 10 window, so go zoom standard to fix your window. And I want you to graph that using nint. So we go math 9 and fill in the details. 3. I will do that.
What are you going for, from 3 to X?
Yeah, 3 to X. And we're in the y equals screen. That's why I'm not in y equals screen. I am now. Math 9. 3. And then tangent X. Your calculator doesn't, it distinguishes between X and T easily, so we're just gonna use X's all the way through. And then he graph.
Anyone else's graph?
Is the plus sign the one after the dx?
Oh, tolerance not met.
Is anybody getting a graph of any kind?
Nope.
Tolerance now.
Yeah.
That's so weird, because mine is.
What you do, if you like your,
I think I might be in, yeah, I'm in degree over.
just go to,
It does do it all. Okay, so graph and you can see the little circle at the top by the battery going round and round and round and round, and we eventually gives you this notation that you guys, for this message that you guys are getting, which is tolerance. So it says, break the function made by hitting the on key. If it's still cranking around, 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 hit the on key if you haven't gotten to the tolerance not met yet. And if you have, then it's on the old calculators, here's what it says. It says graph the function. It says break out of the graph if necessary, because you wait a long, long time and see nothing. This thing finally decided it couldn't do it and told you it couldn't do it. But in the old calculators, it would just keep grinding and grinding and grinding until the battery ran out. It would keep trying to do it. It couldn't do anything and couldn't get it. Recall that the graph of the function y equals tangent x has vertical asymptotes. That's broken. When you've got an infinite discontinuity in a function, and you want to integrate over that discontinuity, calculator can't, because it keeps trying to fill in longer and longer and longer and longer rectangles. They get there, so tolerance isn't met. It says, I can't do this. Okay, so that's the big deal. We've got vertical asymptotes for tangent. When attempting to graph this function that we're looking at, you need to find the piece of tangent that the point 3,5 is on. Because that's the point we have to go through. And there's billions of branches of tangent curves, and we need to find the one that goes through our point. So now we have to recall our trigonometry a little bit here. Okay, and the first branch of tangent is bracketed by two asymptotes located where?
my forces in the negative.
Try again.
Pi
halves and pi halves. Now, because we're talking about the 0.34, and those are just real life numbers, or 3.5, we need to get some numbers for these. What is this? About approximately decimally, what is this?
Negative
1.57? This is 1.57. And so the next asymptote will occur where out here? Yeah, this is -1, -1/2, +1/2, and then that gap right there is pi. So if I go pi units over to here, this will be 3 pi halves, right? And what is that value as a decimal?
3.6
4.712.
Yeah, I have to know that one. So my x value 3 is between here and here, right? Then this is the branch that I want to use to graph. Now, if you set your window to go from pi halves to 3 pi halves, it will still have difficulty because you've set your left and your right side of your window to be right on the asymptotes, and it will still struggle with them. It still views those as a problem. So how could we squeeze in the window just a little smidge?
1.58.
You could, or you could just say pi halves plus 0.001. Type that in your x min. Because you want to go just slightly to get out of that asymptotic problem. So when we go to the window, we're going to go, I'm going to set my x min to be pi divided by 2 plus 0.001. I'm only 1,000th in. That's not going to affect my estimation very much. And what do we want to set this one to be?
Minus.
3 pi halves minus 0.001. Okay, now graph it. We getting anything?
No. Oh, yes.
It's creeping.
Oh, it's starting to creep in a little
It's
bit.
taking a fat minute, bro.
As powerful as these CPUs on these new calculators is, this still takes it a long time.
So that's because you're. Figure it out.
Okay, we'll continue this tomorrow. We may have to regraph this. Don't erase anything unless you have to do your homework. But you got plenty to get started on this assignment. Finish this later.
Finish the activity.